Hi everybody, welcome to our video on the basics of groundwater. Groundwater is super important because it's one of our biggest sources of fresh drinking water. Groundwater makes up roughly 14% of the total water on Earth, which is impressive given how big the oceans are, and it makes up 94% of the liquid fresh water that we have available to us. So that's huge. Most fresh water on Earth is in the ground. It's not in lakes or rivers. So we need that for drinking. It's very important to understand where it is, how it behaves, and how we can protect it, of course. So in the United States, groundwater is used for a number of things. One of the big ones is, of course, public drinking water, about 20%. And then the biggest one is irrigation of agricultural fields. That's about 70% of groundwater in the U.S. Is consumed by irrigation of farm fields. So that's a huge amount. So where does groundwater live? Well, groundwater is trapped in the pore spaces of rocks, obviously below the ground by definition. And we call these aquifers. And this map shows some of the really important aquifers in the United States, which often are associated with specific rock units that extend, of course, across state boundaries, across town boundaries. So another fascinating thing about groundwater is it's really hard to keep track of who owns it and kind of define where exactly it is. Now in this video, I want to focus in on a specific aquifer that we'll use as a case study for many of the points we're going to make about groundwater. And that's called the High Plains Aquifer. It is a single interconnected aquifer that sits at the foot of the Rocky Mountains. So it's mostly in Nebraska, Kansas, Oklahoma, and a little bit of Texas. So this is one big interconnected aquifer, and the water depth varies from about 1 meter to 1,000 meters. So it goes from being really deep to right at the surface. And importantly, we're going to see that this aquifer filled over hundreds of thousands of years from rivers that were coming off the Rockies, bringing water out onto the Great Plains here. And that water was slowly infiltrating into the ground and recharging this aquifer. Now the punchline of this is that today, agriculture and ranching throughout this region are pumping that groundwater out at a rate much, much faster than it can be recharged. So we're basically mining groundwater. It's another resource. And the question is, how much longer can we continue to mine this ancient groundwater before we run out or before the water level becomes too deep to access? So we'll look at some of those questions, and we'll do that with 4 main topics in this video. First, we'll talk about groundwater recharge, so how groundwater actually gets in there. Then we'll talk about the idea of the water table. Then we'll talk about groundwater flow and the hydraulic gradient. And we'll finish by talking about some of the geologic complexities of aquifers. So, of course, groundwater is recharged by precipitation, rainfall and snowfall. And if we look at the High Plains Aquifer, it's right here in the center of the country, and it falls in this belt of relatively low rainfall, kind of about 19 inches per year. Now that really pales in comparison to the Pacific Northwest, where we've got, more than 100 inches per year, and even Vermont, where we live, we've got almost 70 inches per year. So obviously there's just not a lot of rainfall to recharge this aquifer in the first place. And that's really one of the, rainfall is the most important control on aquifer recharge. Now, the other important controls are how well that rainfall can get into the ground. And there's really 3 possible fates of precipitation once it hits the ground. It can run off into rivers. Okay, so the rain falls and it just runs right off into rivers and then into lakes or oceans. It can infiltrate into the groundwater, so that if that water sits around on the surface long enough, it will make its way into the groundwater, which is what we want. Or, of course, it can evaporate back to the atmosphere and become clouds again. So what controls that rate of infiltration? What determines whether a soil or a rock might be good at actually absorbing groundwater? Well, it's controlled by the distribution of pore sizes, usually in soil. And the best aquifers, or the most permeable rocks and soils, are composed of large, well-connected macropores. So what we want is a lot of big pores, so those are the areas between the rock grains that are connected to each other. So the water can flow easily between those pores and not be held by electrostatic forces. So now, depending on the size of the pores and their connectivity, we can define a couple properties of the rock or soil. That would be the porosity and permeability. Okay? Porosity is the percent of open space in the soil or rock. It literally determines the storage capacity of an aquifer. Higher porosity means there's more empty space to put water in. Permeability is equally important. It's the ability of the rock to allow fluid flow. So here, to have permeability, we need to have those pores be really well connected to each other. And of course, porosity and permeability vary widely by rock type. A good example we're all familiar with is sand. Roughly 25% porosity and a relative permeability of about 22. So sand is an example of a material that is both porous and permeable. Clay, or the rock shale, for example, is really interesting. It has a lot of open space, it has a ton of porosity, but because those pores are so small and they're not connected to each other, the permeability is relatively very low. Okay? So sand is a material that could conduct water really well. Clay is a material that cannot conduct water really well. So how does this all fit together? Well, imagine a watershed here, and you've got a soil covering your watershed. During big storm events, of course, or any kind of precipitation, water falls on the surface, and hopefully it makes its way down through what's called the unsaturated zone. And hopefully it travels through that pretty quickly, and then it gets to what's called the water table, which is the upper surface of the groundwater aquifer. Okay? And we can also refer to the area below the water table as the zone of saturation. And once you're in that zone, you're in the groundwater aquifer, and you're sitting just below the water table. So just to recap, we've got the unsaturated zone where water passes through. Then we've got the saturated zone that is the aquifer, where the groundwater lives. And the contact between those is called the water table. So let's go back to our high plains example. How effectively can different parts of the high plains aquifer be recharged? Well, what's fascinating is, depending on the local geology above the aquifer, the recharge rates vary quite a lot. So in the northern part, recharge rates can be up to 100 to 160 millimeters per year. In the southern part, they can be as low, or the central part, they can be as low as 7 millimeters per year. Wow, so that's more than a factor of 10 difference, just depending on the local geologic conditions. And just to put that in perspective, in the central part, that's only about 1% of the mean annual precipitation that actually is able to recharge. In the northern part, it might be up to 20%. So again, not much of that precipitation is making it back into the aquifer. And a final point about recharge, and that is that because recharge is such a slow process, the ideal way to recharge an aquifer is actually with slowly melting snow. If you have a great snowpack that melts back slowly over a couple months in the spring, that's just perfect. That water is delivered slowly to the soil and can be absorbed over those several months. In contrast, really intense rainstorms are bad for recharge because a high percentage of that precipitation just runs off immediately. Basically, the rain is falling faster than the soil can absorb it, so it just runs off into rivers, and it doesn't really effectively recharge the groundwater. So that's an interesting implication. Okay, so now we've talked about recharge. Let's go a little deeper and think about the water table and how that behaves. So the water table is this upper edge of the groundwater, and what's fascinating about it is that it's often not flat, even though it's called a table. It's usually a sloped table. And what determines the regional slope of the water table is usually the topography of the landscape. In particular, we see that the water table is usually governed by the low points on the landscape, where the water table is able to intersect and actually discharge water. So river valleys are usually associated with low points in the water table, and groundwater is usually going to flow from the higher levels towards those lower levels. And so what do we find at those places where groundwater does intersect a river valley, for example? Well, that's where we find springs. Springs are literally the place where the water table intersects the land surface, and water just oozes right back out of the ground. So we see that in this diagram here, and then you can see this spring coming out of a sandstone bed. So we know that the water table intersects the topography surface right about here, and that water just freely flows right back out of the ground. So that's what a spring is. Now, rivers and groundwater can also be connected, and we usually divide them in two different types of connection. So obviously rivers are the low point in the landscape, and so if a river channel is actually below the water table, it's what we call a gaining stream. Literally, the groundwater is discharging into that river and adding water to the flow of the river. And this is really important. A lot of rivers, especially in New England and all over the place, are sustained by groundwater contributions. So if you wonder why a river is still running after a month with no rain, it's almost exclusively because of groundwater contributions in the reaches that are called gaining reaches. Now, in contrast, a losing stream is when the river channel sits above the water table, and so water can potentially flow right through the channel bed and flow into the groundwater. So you might actually lose water from the river into the groundwater. And lakes are just the same. It's actually the case that some lakes are actually basically an extension of the groundwater table. So in this diagram, we see these two lakes here, and we see the water table in blue. And you can see that the water table just intersects right through this low point in the topography and defines the surface of the lake. So some lakes actually are groundwater fed and actually represent the level of the groundwater. Other lakes are sitting above the groundwater. So let's once again try to bring this back to our High Plains Aquifer example. The water table level of the High Plains Aquifer varies a huge amount by, almost 600 or 800 feet from its high point down to its low point. And you can see that the water table height is absolutely controlled by where the big river valleys are. So here's the Little White River, here's Antelope Creek, Rock Creek. Each of these rivers creates a big depression in the landscape. And of course, there's springs where the water table intersects each of these river valleys. And those springs are draining water out of the aquifer, and they're having the effect of lowering the water table regionally. So High Plains Aquifer shows an example of all these processes we've been talking about. So I've mentioned a couple times that groundwater can flow. Let's now take a closer look at what controls the flow of groundwater. And that's going to be something called the hydraulic gradient. So we're going to start this out with a little bit of physics. And if you picture a sloping water table, this upper surface here, And then you imagine what the water beneath that is experiencing. The water beneath either of these points, say point A or point B, is under pressure, and that pressure is called hydrostatic pressure. It comes from the weight of the overlying water column. Literally, this water has weight, and it's exerting it on each parcel of water below it. And so that pressure, or weight, is given by the density of water times gravity times the depth times the area of the water column. So rho gz times area is going to give us the pressure that's being experienced by either one of these water parcels sitting below point A or B. And so that's called the hydrostatic pressure. Now, if the water table is flat, for example, in this horizontal case, the pressure is constant. Each of these parcels would be under a constant hydrostatic pressure. And the water would be stationary. The pressure in the subsurface would be equal, and everything would stay where it is. But once we put a slope on the water table, the pressure starts to vary. So literally, the parcel of water below B is under higher pressure because there's more water above it. A is under lower pressure because there's less water above it. So this sets up a pressure gradient, which we call a hydraulic gradient, between points A and B. And water is always going to flow away from the high pressure under B, and it's going to flow towards lower pressure at A. That's shown by these arrows here. So that pressure difference is called the hydraulic gradient, and to be formal about it, it's the difference in pressure under A minus the pressure under B divided by the horizontal distance. Okay, so now we've got a little more realistic illustration of that. Here's the water table. Here's a parcel under A, which is under higher pressure. Here's a parcel under B, which is under lower pressure. Here's the distance d between them. And of course, the hydraulic gradient is just going to be given by that difference in pressure divided by the distance d. So what controls the rate of water flow down this hydraulic gradient? That's given by something called Darcys Law, which says that discharge from a point, or Q, is proportional to the permeability, K, times the area through which the water is flowing, divided by the viscosity of the water. And keep in mind, we can change viscosity, for example, if we were watching oil flow through an aquifer instead of water. And all of that multiplied by the hydraulic gradient here, which we've already seen is given by the pressure difference between 2 points divided by the distance between them. So, what do we see here? If the hydraulic gradient is steeper, then discharge increases. Likewise, if a rock is more permeable, then discharge would increase. But if the material is more viscous, say oil, this number gets bigger and discharge would actually decrease. So all these variables contribute to how quickly water can move through and what the discharge you'd get from a given point would be. Okay, so now we've talked about how groundwater flows. Let's close this section with one more point. And this is the concept of the confined aquifer. And these are relatively common. What happens is you get a recharge area, for example, up in the mountains, and maybe you have one very permeable unit in particular. So precipitation easily recharges this unit, but then that unit above and below it is confined by a less permeable layer. For example, perhaps a clay-rich shale, which we know has very low permeability. So what happens is that groundwater can still flow, but its path is restricted or confined. And what usually happens is the pressure will build up until it's vented at some lower point. In this case, someone drilled a well down from the surface, penetrated that confined aquifer, and we actually got what's called artesian flow. This the natural pressure gradient, or the hydraulic gradient, is so high here that actually this water is pressurized and is able to flow right back up to the surface, escaping from the confined aquifer. So this is pretty common given the geologic complexity that characterizes a lot of aquifers. And that's a good transition into our final topic, which is the complexity of natural aquifers. So far in this video, we've mostly treated aquifers as if they're a homogeneous medium, maybe a big sandbox through which water can flow equally easily in any direction. Now, any geologist will tell you that's totally wrong. The surface of Earth is not homogeneous. It's made up of lots of different geologic units that all have wildly different permeabilities. And this really exerts a strong control on where and how water can flow. So just looking at this cutaway, for example, we might have some very permeable units in the near surface, things like glacial deposits or river deposits, basically loose sediment that's not even rock. So a lot of those glacial and river deposits tend to be incredibly permeable. Likewise, things like lava flows often have a lot of fractures and are often very, very permeable. But notice all of this is sitting on top of an impermeable layer. This might be a type of bedrock, maybe a granite or a metamorphic rock that has very low permeability and basically acts as a floor below which the groundwater can't really go. And obviously then any hypothetical models of groundwater flow are going to have to account for the fact that there's this huge change in permeability across a surface that has a very irregular shape. So in practice, predicting groundwater flow can be very complicated if the geology is complicated. And so I'll just illustrate that point with a few examples. So one example is from right here in the Middlebury, Vermont area. And our municipal water supply for about 15,000 people plus the college comes from a deposit of coarse glacial sediments right up along the flank of the mountains. There was a big glacial ice sheet in the valley. It left this big deposit of glacial sediments here, which are hundreds of feet deep. They're incredibly permeable, and what happens is we get a lot of groundwater flowing off the metamorphic bedrock coming out of the mountains, and it flows right under these glacial deposits and through them at a very high rate, and we're able to tap enough water out of that at a high enough discharge rate to supply the entire town of Middlebury. So Darcys Law is predicting very high discharge to this municipal water well because it's in these glacial sediments. And then another example, which is fascinating, is the Snake River Plain aquifer. So now we're out in central Idaho. Here's Yellowstone. Here's the Tetons. Sun Valley is over in this area. And the Snake River Plain is a big lava field, basically, made entirely of basalt. And the basalt is incredibly permeable. It's so permeable that these mountain rivers come out of these different ranges and actually disappear. They are literally absorbed. The entire river is consumed into this basalt aquifer. Okay? So we're getting a lot of recharge up here. Then that groundwater flows down the hydraulic gradient and ends up being discharged through springs into the canyon of the Snake River, which is the regional low point in the topography. So here's some illustrations of that. Here's the Big Lost River in Idaho, bringing water that's about to disappear into the lava flows. Here's the lava flows themselves, seen at Craters of the Moon National Park. Doesn't take much to imagine how permeable these fresh lava flows are. And then down gradient, we see huge, massive springs, some of the largest springs in the United States, where this Snake River Plain aquifer intersects the canyon of the Snake River and puts that water back into the Snake River. So basically what's really happening, these rivers are temporarily flowing through the basalt aquifer and then being discharged back through springs into the Snake River. And one more point, what provides the floor of this aquifer? Well, and what defines where these springs come out? It all has to do with the geology. I talked about these thick basalt flows that make up most of the aquifer, but sitting below them is a volcanic rock called rhyolite. It's much less permeable, much less fractured. So compared to the basalt, it's basically an impermeable rock, roughly 10,000 times less permeable. So it acts basically as a barrier or a floor, and most of the aquifer sits in the basalts up above it. All right, so that wraps up our video, and we've talked about 4 things. We talked about groundwater recharge, a very slow process. We talked about the water table and how it interacts with the surface. We talked about what drives groundwater flow and the idea of the hydraulic gradient. And then we just finished looking at some of the geologic complexities of aquifers. So thanks a lot for listening. Here's 3 concept questions to check yourself, and there'll be a quiz at the link below this video. Thanks a lot.